This is going to be video B19. First, here is the problem that we're not going to talk through. And here I'll slowly go through its solution. Oops. And then here is the problem that we'll talk through. All right, you have a potato, it's hot. And you take it out of boiling water, I think, and its initial temperature is 91 degrees. And so that's where the H of 0 comes in. So when T equals 0, the temperature is 91 degrees Celsius. Okay, and the temperature is always greater than 27 degrees. And what they give you is they give you information about how the temperature is changing over time, a differential equation. Okay, and maybe we'll solve this later and find H, okay, the actual temperature at a given time. All right, so the first question is write an equation for the line tangent to the graph of H at t equals 0. Okay, we'll do that first and we'll come back to the second part of this question. So for the equation of a line, all we need is a point and a slope, and at t equals 0, our point is given to us, 0, 91. Our slope is right here. Okay, they gave you your slope, and so we just plug in 0 or 91 where applicable. Okay, so when h is 91, the slope is negative 16. Okay, but then the question is use this equation to approximate the internal temperature of the potato at that time, at t equals 3. And this is what we would have called a linearization, approximating with a linearization. So we are finding, we found this slope. I didn't even finish this problem. We have this point and we write it in point slope form and solve it for h. Okay, so here, this is what I would call the linearization. And we want to approximate the temperature at t equals 3, so I just substitute in t equals 3 and I get the temperature at t equals 3 is approximately 43 degrees Celsius. All right, so then they say, okay, use the second derivative. So the derivative with respect to t of this, we look over here, if I were to distribute that negative 1/4, it's simply a line in slope-intercept form. Okay, and so the second derivative is the derivative of this. The derivative of this is simply negative 1/4, the slope of that line. So use that to determine whether your answer in A, what was it, our answer, whatever A was, it was 43 degrees, is too high or too low, okay, at t equals 3. Okay, so we talked about why the second derivative, the derivative of the original differential equation is negative 1/4. So that means that the curve of h must be, since this is negative, always concave down. Okay, and so up here we found that the slope at t equals 0 was negative, and it's concave down, and so maybe the curve looks something like this, where this is your original temperature, what was that, 93 I think. Okay, here's the line, here's the concave down curve, and sloping down is decreasing, and so at t equals 3 we found too high of an approximation. So this is an overestimate. In part C, they give you an alternate model for this, okay, and it's more complex. Okay, so the change in temperature, this differential equation represents that, and they want g of t, and then they want you to work with that for t equals 3. Okay, but to go from the differential equation to the original, this is what we call a separable differential equation again. And they definitely want to see that you recognize it either by saying it or primarily by doing the work. So we separate the variables. Okay, we antiderive both sides. Don't forget big C. Okay, we're going to use an initial value to find that. And I do want to solve for G. And so you can follow my work in solving for G. Okay, and now I have to find C for this given initial condition at t equals 0 is 91 degrees. Okay, and so I replace G with 91, T with 0, and solve for big C. Plug it back in. Here I have my function, and then all they say is at T equals 3, what would the temperature be? And so I just substitute in a 3 and solve. Okay, so for next time, this is the problem that I'll just show you the work for. So go ahead and try that one. And then this is the problem that we'll do together.